we start with a reminder that there are two flavors of mean. The first is when we know the true population mean, which means we have mu. We have a good idea of what the mean should be, or a good estimate because we've taken many measurements. The other mean is x bar. We use x bar when we have no idea what the value of the mean should be, or we've made less than 20 measurements. And since we have two flavors of mean, that means there's two different standard deviations depending on whether or not we know the true or the population mean or we don't. So this would be population statistics, sample statistics. And in language, we'll use sigma to be the true standard deviation and S our sample standard deviation. Confidence intervals involve the mean, so there's two flavors of confidence intervals. In either case, the confidence interval gives a range of plausible values for a parameter. For example, a 95% confidence intervals indicates that we may be 95% confident that the mean lies in that interval given. In other words, in 19 out of 20 similar samples, the mean would fall within that range. So the first flavor of confidence interval is when we know mu. We have a true value, we know the true value, and we have a good estimate of the standard deviation sigma. In this case, this is how we determine the confidence interval. Note there's a value z. Z is chosen depending on the confidence level that's desired. Most often, we want to go with a 95% confidence interval, so z is 2, or more precisely 1.96. These other variables you know, sigma is our standard deviation, n the number of measurements. If we don't know the true value of the mean, or we just have a sample standard deviation, we use this flavor of confidence interval, where mu has been replaced by x bar, and z has been replaced with t. T is called the student t factor, and it's always greater than z. And t is always greater than the corresponding z, which makes sense because we're not as confident of these measurements. So the interval is necessarily larger. Now here's a table for different values of t that are consistent with a 95% confidence interval. If you want a different level of confidence, you would go to a more expanded table of student t factors. Most often we're dealing with a 95% confidence interval, so this table is sufficient. You also need to know the degrees of freedom. The degrees of freedom are equal to n-1. We should take note of the trend as that as the degrees of freedom increase, as the number of trials increase, our values of t are getting smaller and smaller, and eventually at an infinite number of degrees of freedom, t approaches z. Essentially what that means is that we're moving from sample statistics to population statistics as the number of trials goes to infinity. In other words, the larger the sample, the more closely the confidence interval approaches the same confidence level interval for population. You represent the confidence interval in your charts, in your graphs, presentation of data, as an error bar. The length of the error bar corresponds to the size of your confidence interval. Table. Let's work through a couple examples. Suppose we have a series of replicate measurements, and we have a value for our mean, and we have a value for our confidence interval. How do we appropriately report our result? The important consideration is that the confidence interval determines the significant figures in your reported measurement. The key is that you're limited to 1 sig fig, which in this case limits our result to 2 decimal places. So this is where we start. Our mean value is 26.2345 plus or minus our confidence interval 0.0245. Now, as we mentioned, we can only use 1 sig fig in our confidence interval, which here means we can use 2 decimal places. We need to match the decimal places in the confidence interval versus our mean. So in this case, each of these numbers are rounded down, and our final answer, correctly reported answer, is 26.23 plus or minus 0.02 milligrams per milliliter. Or if we want, we can write this as 26.23 plus or minus 0.02 milligrams per milliliter. Let's discuss some incorrect responses and why they're incorrect. In this first case, there's too many decimal places. This is the last known decimal place, and it's not reasonable to report beyond the last known decimal place. In this second case, we're not matching decimal places. This answer should be to the 2 decimal places. Let's work through the second problem. We're measuring percent nickel in the sample. We made 4 measurements and we got the following results. We determined the sample mean of those 4 points and the sample standard deviation. The question is, what do we report as the 95% confidence interval? We start with our sample confidence interval because we only have 4 trials, and therefore we're going to have to find our appropriate value for the student t factor. We do have the standard deviation, the sample standard deviation, and we have our number of trials, which is 4. We look back to our previous table for about 95% t factor for n minus 1 equals 3, we get t is 1.81. So we can plug that into our calculation. All right, so we plug in our value for t and churn out our result. We see mu is equal to our x bar value, our average. X bar plus or minus, all of this comes down to 0.00065. So now we need to report our answer. Okay, we can only use 1 sig fig, and that means we use 1, 2, 3, 4 decimal places for each of these. So we have mu is equal to 0.0326 plus or minus 0.0007. Our unit is percent.